It's recording.
Okay. So I'll share my screen. Is it visible now?
Yes, this looks
Okay.
good.
Okay. Okay. Thank you, Liang, for inviting me to this quantum computing seminar series. It's my honor and pleasure to share the research that we have been doing on this topic. And to the audience, good morning, good evening, depending on from where you are logging in. I do see a couple of familiar names, and I see one of my former students here, actually, Dr. Aisha Khalid from Queen's University, Belfast. So, hi, Aisha. We have been working on different topics, and some of this I will present here, which we initiated long time back when she was my PhD student. Okay, so coming to the discussion topic, I will like to present what I say as a brave new quantum world. And I call it brave new quantum world because there are lots of very fast moving innovations happening in this domain, and there are lots of uncertainties that we are facing. It's definitely as tumultuous as AI in the past, or it's happening right now with the AI, but in quantum, we are looking towards the future. And there are issues that we don't have solutions yet. We don't know how it will lead to, but yet, as researchers, we are just moving ahead. And some of the observations and studies that we have done in this domain, I will share it with you. So, to just briefly introduce what kind of research that we are involved in, our group is somehow spans a bit on interdisciplinary, and I'm sure you will be able to relate on many topics that we are engaged in. So I like to present that in this typical quad chart where no matter what you do, it is trying to solve some kind of very fundamental algorithms on a processing machine. And this algorithm is eventually being executed on some kind of technology. So this is the connection between the math and the physics, or the math and the biology, depending on what media that you are putting in. So this algorithm to technology mapping is enabled by having a system which is a higher level of abstraction that we can operate, we can interact with, because it's not possible anymore that you go to the low level and starts operating on the semiconductors directly. But you need some kind of user interface and a programming model and flexibility of an instruction set. So this is what the system provides. And this all things are deeply connected through many different kinds of automation flows. So I have been primarily working on the system and automation, but you can't design a system without having a fundamental goal of advancing an algorithm, or without knowing to what kind of technology you are mapping. So I have been closely collaborating with expert groups in the algorithm and technology to help us define the technology pull and application push, this kind of effects. So in the algorithms, I had started long back working on the wireless receivers, then on the cryptography. I participated in some numerical linear algebra kernel studies and modifications of that. Some work in bioinformatics, and of late, of course, on AI. And on the technology front, I definitely, like all of us, we have been following the evolution of CMOS, and then I delved on in-memory computing fabrics, and the topic of today's discussion on quantum computing. In the system, we worked on heterogeneous system on chip, application-specific processors, CGRA, reconfigurable processors, and all of these are enabled by many different kinds of automations like ASIC synthesis, high-level synthesis, logic synthesis, technology mapping, reliability estimation. So this set of tools help us to also navigate whenever a new technology comes into picture or a new algorithm comes into picture. So this is the briefly our journey across different domains and different quadrants. Coming to the core topic of today, I divide this talk in two parts, and one is on the quantum computing, and the other is on the post-quantum cryptography. So they are basically two sides of the same coin, particularly if you look at from the security perspective. So in the quantum computing, the first and most important question is why quantum? And why do we actually need it? What kind of problems it's solving? And to give a brief perspective, I'm sure most of you are aware of that we look into the quantum computing primarily in a broad division of two kinds of quantum computers. One is the universal quantum computers, which is akin to general purpose processor, for which we see that there are algorithms that are being developed dominantly from the Shor's algorithms and Grover's algorithm, and that is something which we see as relevant for our security discussions. On the other hand, we do have quantum computers which are specialized for certain hard optimization problems that's similar to an ASIC. And on that domain, D-Wave is one of the companies which is championing these quantum annealing machines. But their claims are often questioned, and there is studies by groups which say there is no evidence of quantum speed up, there is no evidence of actual quantum superposition or entanglement happening. But on the other hand, there are studies which showed that for simulated annealing or quantum Monte Carlo, there is a demonstrated speed up. So those kind of speed ups are also uh, questioned sometimes because the speed up comes at a very heavy energy budget, which could be alternatively achieved by classical computing, for example, by the advances in probabilistic computing, which recently has been demonstrated by groups of Supriyo Dotto and Kerem Kamsari. So this is the very basic tension that we do observe in the advance in quantum computing, that how much improvement is really an improvement, whether it makes sense or not. Shall we still keep with classical computing or shall we champion quantum computing? And one of the very nice resources about that is the quantum algorithm zoo, where you can go and you can actually look for many different algorithms for which there are quantum variants for which there is a claimed improvement over the corresponding classical one. But there is also a nice summary in the quantum algorithm zoo that for certain algorithms, the classical strikes back and that shows further improvement matching the quantum speed up. So the difference, the gap kind of vanishes. So this is particularly the question that many people do have in the quantum domain, is that we are talking about the quantum advantage, we are talking about quantum supremacy, but is it real? And what we see is that there are algorithms in the quantum algorithm zoo, which are noted to have polynomial, super polynomial, exponential speed ups over classical, but occasionally they are having setbacks with the dequantization. And there has been very thorough studies about the memory requirement for certain applications like HHL quantum algorithms. They can be suffering from the IO limitations, which may not let this HHL algorithm to fully demonstrate its claimed improvement over the classical one. Similarly, one of the very well studied and well researched algorithms for quantum optimization is QaOA, which briefly enjoyed a better approximation ratio than known polynomial time classical algorithms. But this was short lived because the classical algorithms came back again. So the kind of summary that we are getting in is that unless we have an exponential quantum speed up, or at least a super polynomial quantum speed up, we may not be able to hold its advantage on a practical setting. So this is something also which is heavily being studied by quantum algorithm developers, quantum complexity experts, and they put a claim, like if you look into the polynomial hierarchy, that we have a particular space that we call as a BQP, or bounded error quantum polynomial time, which has been shown to have a oracle separation with the NP set. That means there are certain problems which, on the basis of a particular oracle, could be shown to be not contained in NP. But those problems, on the other hand, are yet to be connected with a practical application. So this back and forth is ongoing. And that brings us to the, again, the fundamental question that we are working so much on the quantum, and there are so many different kinds of problems we are solving. Of course, it's a technological wonder that we are able to manipulate devices at the quantum scale and perform computation, but what it is it for? And one of the very well-known algorithms from Peter Shor and called Shor's algorithm that gives a answer to this, that okay, at least we do have a simple super polynomial improvement over classical algorithm for two computationally hard problems, discrete logarithm and factorization. And for these problems, we have a very practical use case, although not on the good side, but on the bad side, that if we are able to run those on a quantum computer, we can break uh, public key cryptography algorithms, which are standardized right now and which form the basis of a lot of security protocols. So it's safe to say almost everything in the digital world going on right now will be under a lot of, say, threat when we have a large scale uh, quantum computers running Shor's algorithm. And this is a practical evaluation of that, calling an attack complexity estimate. This study has been done in 2019, published by a consensus study report in National Academies Press. But this is something which keeps on getting improved and improved. So the thing that's to be highlighted here is if you look into the crypto systems like RSA and ECC, which are predominantly two public cryptographic algorithms, then they can be broken in a matter of few hours, and that calls the entire security protocols and everything which is relying on this algorithms under question, that shall we keep running this. On the other hand, there are private key crypto systems like AES, for which we can get some improvement by running Grover's algorithm, but it's way beyond any practical attack setting, because it still needs like millions and billions of years. So one of the definite threats that we are having here is to break the public crypto system. The saving grace in that matter, as of now, is that we need to build really large quantum computers, which requires like millions or more physical qubits, because in the quantum computer, one of the metric of the scale is the number of qubits, which is kind of equivalent to a classical bit. So logically, we need few thousand qubits, but the qubits, they being leaky, we need to wrap those arounds with error correcting code, and correspondingly, there needs to be a list of like 1,000 times more qubit per logical qubit, according to the prominent surface, the error correcting codes, due to which we do see that there are millions of physical qubits needed. To bring that into perspective, right now for the universal quantum computer, we are at the scale of 1,000 qubits or so. But I'll come to that and how we are growing and how we are scaling up on the quantum computer capabilities. But this is a real threat. And although it's not, again, it's a positive use case, but it's a thing that we should be worried about, because unless someone builds it, we are always at the mercy of some malicious actor or an adversary building such a quantum computer, and can completely turn every security protocol upside down uh, by breaking these algorithms. So coming to the scale, we know that we have enjoyed a significant advantage over years and decades due to Moore's law. And there are many proponents of quantum computers who see this as being repeated also with a significant growth uh, over years in terms of quantum computers as well. And this has been formulated by Google with a Nevin's law, uh, named after Hartmut Neven, who observed that this quantum computer capabilities is also growing at similar scale as we have seen the Moore's law. So this, of course, calls for a lot of technological jugglery, that people need to come together to achieve a very good quality qubits and excellent error correcting codes, and performance of the gates, quantum gate operations with high fidelity. All these things needs to be there, but the scale is being maintained, and this is also uh, observable from the development roadmap that is projected by IBM. So you can see that IBM last year or actually in 2023, towards the end, they did release this IBM Condor, which was 1121 qubits, and they are coming up with the newer machines like Heron and so on that goes into 1000 plus qubit, and they project this to be in the realm of million qubits by 2025. So with this growth, we can assume that the kind of million qubits needed for practically threatening uh, public key crypto system is not in distant future. The consensus varies, but everyone says, okay, within 5 to 7 years, we will be in that range. So right now, this is not yet, say, noise resilient. The quantum gates are noisy. There are lots of errors in the qubits, but at least the scale up and having the qubits in the superposition state, maintaining the gate operations for longer duration, these things are being achieved. So coming to the basics of this, again, I'm sure most of you are familiar with this. I'll just quickly revise that in a quantum computer, we have this basic building block called qubit, where we can have a simple two-level system, which can be represented by, let's say, an electron upspin and downspin. For different technologies, the two-level system are represented in different ways. But the magical thing in the quantum world is that it can be at the 0 or 1 state in a superposition where the 0 state is represented with a probability and 1 state is represented with another probability, with the condition that the square of this probability, when added and taken a square root of, it represents 1. So this can be pushed further to multi-level systems where instead of qubit, we call it qtrit or qdit, depending on how many levels we go. And one of the misconceptions that we often do have is that it is staying in both states. That means it's operating on the both states. But that's not true. We basically do manipulate the amplitude, which is represented in the probabilities in the quantum states. But that itself is a very powerful thing, and we can modify the amplitudes of all the qubits which are in the superposition by applying the gates. So unlike or similar to what we observed in the first era of classical computing, in quantum also, there are many different technologies that are being, say, promoted by different companies, different research groups to achieve the qubit and superposition and quantum gate states. Those are based on superconducting, solid state, photonic, ion trap, and neutral atom. So all these technologies, they have their own pros and cons. So people are trying to come up with the best technology that will give the ideal long-term, low fidelity, low error qubit realization. Once we have these qubits, then we operate on the qubits by using so-called quantum gates. So one qubit can be represented in so-called block sphere in an initial state. By applying some gate pulses on the block sphere, we can put the qubit in a different final state. So applying this gate pulses can also be represented in a matrix format. And there are many different gates for the quantum state, like Pauli gates, Hadamard gates, phase gates. There are some gates which are named after the scientists who were working initially in this domain. Like we have Toffoli gate, which is basically a CC naught. C stands for control. And these lines that you see horizontally are the qubits. So when we apply a gate pulse involving these 3 qubits, then the third qubit will change its state from 0 to 1 or 1 to 0, depending on if both the first and second qubits are 1. That's why it's control, control not, and it's Toffoli gate. Now, this number of control points can be extended, and we get into so-called multi-control Toffoli. Instead of a simple NOT operation, we can have a Z operation, and then it becomes control Z or CCZ. Similarly, we can have a swap operation. We can have phase gates. All of these operations can have a matrix representations. And some of this matrix representation, as you can see, involves imaginary values. That means we are operating in the block sphere. And this is not something which we can have a classical equivalent. But for some of them, like the swap gate or for the CC naught gate, it is almost equivalent to a classical operation. So when we have two of these values operating on this, then first and second qubit basically can be summed up as an AND operation. If both of these are true, then the output gets resolved. So this helps us to connect with a lot of classical circuit building logic synthesis techniques. Now, another important thing to note here is when we build these quantum computers, then some of these gates can be termed or clubbed together to form so-called universal gate set. So this is similar to what we have in the classical computing, and NAND is universal. In the quantum domain, we also do have Clifford group like Hadamard and Synod. Those form an universal gate set. There are other several universal gate set, but we currently heavily work on the Clifford group for one reason, that they do have efficient fault tolerant implementation in multiple different technologies, because it's not sufficient to just have the gate operation, but the gate also must be applied in a fault tolerant manner. So this is particularly a recurring theme in the quantum world, because when we are operating in the quantum domain of physics, then the noise or the environmental variations or any kind of external impact has significant effect on the computation flow. For that reason, we have to be very careful about the qubits leaking the value over time, or the gates not being applied properly. So this brings us to a significant, say, chunk of work that we call in the quantum error correction codes or fault tolerant implementation at the low level. So this whole thing also is termed collectively as noisy or intermediate scale computing, or so-called NISC. This is the term coined by physicist John Preskill, who maintained that right now we are dealing with hundreds or at most 1,000 qubit, but these qubits are noisy, and we have to uh, take care of this noise that's being built up by applying either multiple separate operations, executions, and doing repeated measurements, or we have to live with this noise and expect the output to be an approximation of what it could be in the ideal scenario. But we may do also gain something out of this noisy quantum computers already. And this is something that Preskill challenged the whole quantum community, that are we able to identify high impact applications which are solvable with the noisy intermediate scale quantum computers? Like, can we get quantum machine learning or financial portfolio optimization, which has a, say, algorithmic improvement over classical with polynomial, super polynomial, exponential speed up? If we do have that, can we translate that improvement or advantage already within a few qubits in the NISQ era? So it turns out that if we want to realize that, then we need to develop low depth quantum circuits, because the circuit depth in the classical sense, it can be translated also in the quantum. If the circuit depth increases, the noise buildup also is increasing. So we definitely need to have shallow quantum circuits, and that again translates into properly cut out work for the EDA experts who have been working on technology mapping, logic synthesis in classical, that can we do a synthesis and mapping that uses less gates, that follows certain constraints like nearest neighbor to minimize the noise? Can it avoid noisy qubits? Can it perform technology mapping to control all these things? So this brings us to the challenge of design automation for quantum computing. And I have been working on this topic for a while. So I will share some of the summary improvements that which we contributed to, and in general that people have been working on. So this is practically realizable because there are already commercial quantum computers, and many of you are aware of, let's say, IBM Qiskit, a fully open source flow. You can access this IBM machines through Amazon. Then there are Rigetti, Xanadu, also these machines on which you can write a quantum algorithm and perform so-called transpilation that maps the algorithm onto low-level gate pulses, which runs on a real quantum computer. So this mapping and the transpilation is akin to what we do in the classical logic synthesis technology mapping, or in the general purpose computers, what we do as a compilation. Same thing, and the flows here are shown here, which starts from a quantum algorithm implemented in some quantum programming language like Q Sharp or Project Q, translates using quantum compilation, which uses various libraries and optimizations by finally mapping into a target platform. So this quantum compilation, again, it could be split into multiple levels, that you start with a simple description of the algorithm that you want to run. And the algorithm, in the heart of many quantum algorithms, the kernels could be some arithmetic operation like integer division, which you can represent using older or known programming languages like Python or Verilog. And then you run the logic synthesis, followed by so-called reversible logic synthesis that maps this logic operations into some kind of reversible circuit. We call this reversible because the quantum gates can be bidirectional, that if you have a control not operation, you can go from the input to output, and you can also uniquely find the input from the output. So it's bidirectional. That's why in the first generation of quantum compilation, people were calling those as reversible logic synthesis operation. So there has been several developments in the logic synthesis, reversible synthesis, and technology mapping, which is captured in this flow and which has been available through IBM Qiskit or open source tools like Stack tool flow. These academic toolkits are there. And people have been developing different point tools targeting different machines. Like if you're working on neutral atom quantum computing, you might need to solve a very specific technology mapping problem, and that has been independently developed, mapping to their quantum computers. So some of the highlights that people have worked on, and some of this that we also contributed, is we definitely start from classical logic, which could be Boolean logic. You represent that in truth tables and binary decision diagrams. And then from this, you try to convert that into an equivalent quantum gate set, where you might want to run specific circuit optimization. You might want to minimize the additional qubits, which we call as an ancilla. And of course, the number of qubits impact the cost associated with the quantum computers. Then there has been some very significant works that realizes quantum circuits with an unit T depth. T gate is one of the gates in the Clifford plus T set. Then we very recently we studied on the space depth trade-off for multi-control Toffoli gates, and how can we map onto any T depth that you want. You may say, okay, I will allow for 5 extra ancillas and I want to have minimum T depth. So this trade-off can be very nicely captured in a very recent algorithms that we have developed. So that just represents the first stage of the quantum circuit mapping. And while doing this, we found that we can leverage a lot from our knowledge in the classical logic synthesis. Like in the classical logic synthesis, we do have a lot of different intermediate representation, which starts from LUT-based representation, binary decision diagrams, truth tables, and inverter graph, XOR inverter graph. But broad classification of this intermediate representation is that some of these are structural, like AIG, XAG. These are a structural representation. And some of these are functional, like truth tables and BDDs. The structural representations are scalable, very easy to manipulate, but very hard to obtain a very compact output, like an optimal output with some guarantees in the structural view, which is something we can do in truth tables and decision diagrams, but they are not easy to scale up. So one study that we did in the early days of the quantum computing mapping is to mix the structural and functional logic synthesis, where you represent the whole algorithm in a structural format, find the small blocks within it that you want to optimize, and take it out, perform the guaranteed optimal synthesis in terms of depth or number of qubits, and then stitch it back to the original data structure. So this is like an hybrid logic synthesis. But very recently, it has been shown that LUT-based and XOR and graph-based synthesis, they also achieve very nice performance in terms of the quantum circuit synthesis part. The next part in the quantum ADA domain is on the technology mapping. And one of the first problems that people identified is if you are looking into the qubits, and here the lines are like qubits, and sometimes you perform the gate operations like control NOT operation across long distant qubits. So this is not something which is desirable in a quantum platform because long distance gates, they can have low fidelity. They might not be applicable because there is no connection between the distant qubits. And you might have to apply the connection step by step by adding some kind of swap gates in between. So this conversion of distant gates to local gates can be achieved by having a swap gate first, then perform the local operation, and then again swap those back to their original locations so that you can continue on the operation step by step. But this problem of converting distant gates local while maintaining a very low depth is shown to be an NP-complete problem. So we are resorting to different heuristics. And one of the heuristics that we worked on is called look-ahead scheme that was shown to work pretty well in practice. So this look-ahead scheme is primarily at the core of this nearest neighbor mapping that we see right now in IBM Qiskit. But this kind of solving for nearest neighbor and localization, that is only shown in the first range of results for a very simple qubit orientation where you can assume that the qubits are just arranged one after another. But in reality, the qubits can have many different kinds of connections. And for that, the concept of which gates or which qubits are neighboring and which qubits can be connected on a distant gates, that varies differently. So in order to map a particular quantum circuit on a particular platform, it turns out that we have to solve a graph to graph mapping problem while achieving nearest neighbor. So for this, we could achieve something called a depth optimal solution with an integer linear programming formulation that also scales pretty well. So the ILP constants are nicely summarized. So in a follow-up of this works, it turns out that the topology constraints or the swap operation is not the only thing, but we also have to be aware that the qubits, which are forming like building blocks in a quantum computer, may have different quality. Some of the qubits are good qubits, some bad qubits, some are leaking, and we want to avoid those. And we also want to apply the gates on the qubit, which will result into high fidelity gates. So if I am not avoiding this bad qubits, then I may end up having erroneous results. So this is called a fidelity aware mapping flow. And we came up with a combined flow that goes through the entire thing in one single, say, phase-wise mapping, where we take the input quantum circuits, take the quantum computer topology, and then we know that the input quantum circuit needs 4 qubits, whereas the connectivity graph from IBM Melbourne has 16 qubits. So out of this 16, we have to take only 4. So you choose a particular subgraph from this. Then you map the qubits one by one, like L1 could be mapped to 0, L2 could be mapped to 1, L3 to 13, and L4 to 2. So it's like a T formation, but you can also have a square formation. So many different subgraph and you take the formation. After you do the mapping, you do the nearest neighbor compliant circuit, and finally fidelity aware mapping to achieve the best quality qubits together. So all of these phases needs to be run multiple times, and we have shown in that flow that if you do the careful mapping from phase 1 to phase 4, the fidelity of the final result can be significantly different by even one order of magnitude. So this is the logic synthesis and EDF flows of the quantum computers, which we kind of take by default to exist now for IBM. But yet this is a serious problem for emerging technologies like neutral atom. This flow is not yet very stable, or for Rigetti, this is not yet stable. So every different technology, they bring their own mapping and challenges in the synthesis which needs to be solved. But that's only the part of the story. Once we have a stable mapping, then the next problem becomes, okay, I have to start mapping real circuits. And by real circuit, we were exclusively focusing on the source factorization and quantum cryptanalysis, because this is something where we do see that the advantage over classical is real. It has practical implications on the security protocol. So this is the domain that we focused on. And while we looking into that, we figured out that one of the very important building blocks in the Shor's algorithm is arithmetic, which starts from the adder, and then you will need squaring, you will need division, you need multiplication, modular exponentiation, everything. So when we started looking into this, we figured out that if I just try to represent different kinds of adders by drawing parallels from classical adders, there is a wide-ranging variation that people have not explored yet. So we started mapping based on the properties of an quantum circuit, like the T count and the T depth and the qubit count. And we could uncover some new configurations based on higher radix mapping, based on modular addition, based on Cogestone, Han-Carlson. So all these classical adder principles we mapped onto the quantum circuits, explore different strategies of in place, out of place, uncomputation, picking up to fully modular or non-modular. And now we do have a wide-ranging IPs on quantum arithmetic so that we can start building the next phase, which we are working on at this moment. But of course, when we work on these problems, then we do get a feeling that we are still dealing with simulations. And what about running a real quantum hardware? And this is actually based on that, we had a fun project because there is a quantum computer available in the Center of Quantum Technologies, which is being developed by researchers at A-Star Singapore and National University of Singapore. And they said, oh, we have an ion trap quantum computer. And we said, okay, we can attack that. And this is purely fun project because this quantum computers at Center of Quantum Technologies is only 1 qubit and 2 qubits. So you can't really start mapping your adders. No way. And on the other hand, when we start doing this in the IBM machine, it's in cloud. So we really don't get the feeling of running things hands-on. So we said, okay, we will attack your machine. And it will be a very simple malware attack. And this is what we know to be the first claim to have a malware running on a quantum computer. So what does this do is, it's actually idea is pretty simple. We have an ion trap device, and this ion trap device is receiving inputs from so-called digital synthesizer, which is being controlled by an FPGA, and FPGA is being controlled by a target CPU. So no one is going and writing the quantum computer with a quantum keyboard. It's at the end, it starts from a classical CPU. And if you are not careful enough, then the classical CPU could be infected with a malware. And that's exactly what we did. And the researcher who was working on the target CPU, and we just told that, okay, can you click on this particular phishing mail? Of course, many people do this accidentally, or you can put it in USB. So we delivered a malware, and that malware, which we designed in-house, that could bypass typical network intrusion detection tests. And that was able to get running into the target CPU. And of course, once we had the control of the CPU, we could do many, many things. The simple thing that we did is we started varying the control scripts that's going into the FPGA, which are fixing the amplitude and the different durations of the pulses, which are going to control the ion trap device. So their single and 2 qubit devices were running basic quantum machine learning based on so-called re-uploading scheme, and they were able to classify. But then when we put the malware, we manipulated the amplitude, and then it turns out that the classification accuracy significantly drops. So we are able to infect the quantum computer through the classical front. And we were able to do it also in a stealthy manner. Basically, after every modification of the amplitude, we were uh, recovering the old amplitude file just after the information goes to the FPGA. So there are many different parts of the complete communication from the FPGA to DDS, DDS to interrupt device, or even the DDS measurement coming back to the CPUs. These are the things that we can start manipulating. Now, this is still on a small quantum computers, and another very recent work that we did on cloud-based quantum computers, where people have been toying around with the ideas that if you have a multi-tenant cloud quantum computer, which is going to be very relevant because large-scale quantum platforms are having 1,000 or few hundred qubits, and they of course would like to engage as many quantum circuits running on this full quantum computers as possible. So if you have 127 qubits, you don't want to have the other qubits remaining idle. And you want to run, okay, put 5 qubit circuit here, put 4 qubit circuit here. So when we have this multiple different qubit circuits or different quantum blocks, they start affecting each other. So this has been well studied, and there has been several papers prominently by the group of in UT Dallas, in the group of Yale, and the group of Penn State. They have reported these findings. But what we saw is that their claims are still relying on the assumption that if we keep enough separation, enough gap between two different quantum circuits, then the effect will vanish. But we observe that this is not really true. And you can have a particular set of qubits which are what we call as victim qubits, which is, let's say, having at a qubit position 0 and qubit position 108, which is far apart. And then you put some attack qubits which are position 60 to position 70, which are, or sorry, the other way around. The victim qubits are from 60 to 70 in this range, and the attack qubits are in a different range. So what we observed is that if the attack qubits are even far apart from the victim qubits, they start influencing each other, basically because during the operation, they create a swap path. So when the two swap paths of the attack circuits and the victim circuit, they have an intersection, then we see a significant degradation of the results. And we observed it by running Grover's algorithm, by Simon's algorithm, and we tried this with uh, active attacks. That means the victim is being manipulated by the attacker, or passive attacks, where the attacker's only interest is to learn something about the victim qubit and quantum circuit. We replicated that for the IBM machine, on the Rigetti machine, all on Amazon quantum computers, and we see it to be a real threat. So this is not particularly about building the quantum computers and arithmetic and factorization and so on. So we are progressing on that. But here we see there is an easy way a classical attacker can actually hark back the quantum computers and tell, oh, okay, fine, you are doing Shor's algorithm to break classical. We can do something also to break you. So this interplay is what we do observe. So this brings me to the second part, and we are on the way. And I know that there will be definitely some practical breakage or breaking of public key crypto systems in within a decade for sure. And the current prediction is few million qubits that can break within few hours, RSA and ACC. We are on path, on the course to go that. So that brings us to the topic of so-called post-quantum cryptography. So what is post-quantum cryptography? Is we know that the public key cryptography is at the cornerstone of any digital communication between untrusted parties, be it gaming, e-commerce, social network, net banking, and everything. So if we are having a discussion between Alice and Bob, then we need to have a digital signature. We need to have a key exchange between the encryption and SIMs, so where the session key is being established. So although private cryptography is secure from quantum computers, private cryptography by itself is not sufficient. We need to have the public cryptography sitting on top of it. And the public key cryptography, PKC, that prominently is being used today is from RSA and ECC, which relies on the hardness of prime factorization problem and discrete logarithmic problem, for which, as of now, there are no polynomial time algorithms to solve this on classical computers. But we do have the quantum computers, which is suddenly becoming super powerful with Shor's algorithm, and we know it's scaling well. We know that we can fix the errors like the quantum noise that's being developed. So we can scale up and we can go to a full fault tolerant, noise resilient quantum computer that is serious threat to public key cryptography. So realizing that threat, in 2016, NIST that started calling for proposals for standardizing post-quantum cryptography. And in post-quantum cryptography means that we have to develop some public key crypto algorithms which are quantum safe. So this kept on running in parallel with so-called quantum key distribution or QKD. So QKD has been growing over years. People can set up fiber optic links between distant points, and they can transfer the information between two different sender and receiver or repeater nodes using quantum communication. That's what quantum key distribution is about. But despite that tremendous the advance of quantum key distribution, it is well known that you cannot live by just QKD alone because you are not expected to have a quantum key distribution sender or receiver in your smartphone or in your IoT device. So you definitely need a stack which is relying on the classical communication infrastructure that goes with the post-quantum cryptography. So starting from 2016, we are progressing, and in 2024, the first draft standards for PQC has been released by NIST, which is still ongoing with many more new inclusions in the standard, which is supposed to happen in the coming years. The expectation is that one should be prepared with a fully quantum safe crypto system by 2030, so on, where we know at that time RSA DCC will be broken by quantum computers. So that's the vision of NIST. They release the standard, and similar standards do come up with also in China. There is a standardization initiative. In Europe, there is a standardization also, which is slightly different from the NIST. There are many nations around the world which are adopting their own standards or following the NIST standards. Like South Korea is having its own PQC contest. But everyone does realize that they need something called quantum safe crypto system. So from 2017 to until 2024, the first standardization efforts eventually led in US and in Germany, the PKE or the key exchange schemes like Kyber, Frodo-Chem, Classic Macalis, and some digital signatures like Dilithium, Falcon, Sphinx, XMSS, and LMS. So they are color coded to show that the standardization bodies are trying to split the risk in multiple baskets. Baskets means these algorithms, they do rely on the assumption that certain problems are mathematically very hard even by a quantum computer to break. And these problems stem from code-based cryptography, hash-based crypto systems, or lattice-based cryptography. So it may happen, it's not ruled out, it may happen that a lattice-based crypto system gets broken by a polynomial time quantum algorithm. All of this depends on whether we can find something that belongs to BQP and not in NP, or whether polynomial hierarchy remains or completely fades out. These are bigger questions, but the standardization bodies are propagating the idea of so-called crypto agility to have support of multiple different cryptographic schemes coming from different mathematically hard problems. So the particular research that we have been working on is to look into the side channel attacks of post-quantum cryptography. So side channel attack is relatively a recent discovery, I would say. In early 2000, it was found that it's not sufficient to have a crypto system robust by purely mathematical sense. Because when you are implementing the cryptographic scheme on a physical platform, then you also do leak a lot of information in form of power consumption, electromagnetic waves, timing information, and this leakage is sufficient to break the crypto system even though it's mathematically hard. So based on that, when the NIST was doing the PQC standardization, they did emphasize that the crypto systems has to show efficient implementation that is analyzed rigorously for side channel attacks and must have some kind of countermeasures that resist such attacks. So we do have the state of the art equipment to perform such attacks. Many of these attacks are actually evaluated when one goes for the cryptographic implementation to be standardized by, for example, common criteria evaluation or FIPS standard evaluations. So this research is now culminating towards something that we call as a quantum safe migration, because we know that the quantum computer is a threat to public cryptography. We know that the algorithms needed for quantum safe cryptography is being built, but just having the IPs and algorithm is not the complete story, because we are now looking at a huge digital infrastructure across the world that has been supported by RSA and ECC for last 50 years. And we have to switch over everything from that step to the new step. So this whole quantum safe migration basically can be summarized over this kind of cone, where at the heart there is a hardware crypto accelerator, software crypto libraries using the post-quantum cryptographic architecture, but they are not enough by themselves. It powers the security protocols, security objects, and interface, and then it goes on to the security solutions and services like VPNs, hardware security modules, web servers, and client, which eventually blossoms to the application domain that the users visualize, like consumer electronics, automotive. So this entire journey has to be taken over for any quantum safe migration. So when we look into the migration, then there has been studies by most of the consulting firms uh, promoting on what kind of applications should be immediately migrated, what should be migrated later. And what they say here is that there are systems which has very long life cycle, and there are data that also has a long life cycle. So the ones which are having the longest life cycle in data and system, like banking or insurance, this kind of systems has to go through the conversion soonest, because they are already being harnessed by malicious actors to gain some kind of information from. And we call this kind of attack as harvest now, decrypt later. So to give an idea that, let's say if there is an insurance data which is considered highly sensitive and must be preserved for 30 years. So this kind of data shelf life is recommended by many standards for insurance standards. So which means that there is already a lot of data that's being stored now today in 2025 that has to be accessible for 30 years. That means till 2055. So, and if right now we are encrypting the data using RSA and ECC, then people can just collect those data, which is encrypted with this quantum vulnerable crypto system. And then when the quantum computer becomes available, let's say in 10 years, they can recover all the secrets from those. So this is the harvest now, decrypt later attack that one must be uh, aware of. So considering this whole problem of the quantum migration, we particularly did focus on the design of the built-in crypto system called lattice-based cryptography, which is at the heart of two of the standardized post-quantum cryptography schemes called Kyber and Dilithium. So we did a lot of studies on the physical attacks, corresponding countermeasures, side channel attacks, fault injection attacks, and I will talk a bit about on the backdoors that we also discovered on some of these crypto systems. We worked on the optimized implementations on GPUs, on FPGAs, and also ASICs for this lattice-based cryptography. And when we look into this migration, then there are many different challenges, and I will highlight a couple of challenges. One that we discovered last year, we call it a particular attack called Kyber Slash. And to understand this attack, we have to go through a bit of how the decryption operates in the Kyber crypto system. Is that if you have this particular cipher text, which is a tuple with U and V, and it takes in the secret text to generate an erroneous message polynomial, and then it's decoded in this particular step to produce the final plain text message. And we know that this V minus US is a step where we have the erroneous message polynomial that can be also represented as enc M plus ES prime, E double prime, E prime S. So this particular error removal is what is being done in the decoding step during the decryption. And this can be alternatively termed as a decompression from a lower modulus to higher modulus. When we do this operation on, let's say, a microprocessor on an Intel platform, like Intel x86 platform, then this decryption operation involves an integer division. It turns out that division instruction that is invoked if you are compiling the code with GCC with minus OS in Intel 86 is a variable time division. And the variable time division will take d clock cycles if n, it is the numerator of the secret numerator, is less than 3329, it will take d clock cycle. It will take 20 more clock cycles if it is more than 3329. A typical division instruction in x86 that's optimized for the implementation. But what's happening here is that one is just running the decryption multiple times and they are able to gather sufficient number of IDV execution, which leaks the secret about n, whether it's taking d or d plus 20 clock cycles. So that's the timing information that one can capture. We identified that as a Kyber slash timing vulnerability. So this is a very practical problem that people do face when they take an open source code and they start implementing their own quantum safe software. So it turned out that this particular Kyber slash was already affecting a lot of different servers, and there are major companies which had to patch it very quickly in order to keep the secret a real secret. So this is one of the problems that we discovered, and there are many more which we saw through the side channel attack. The other very interesting thing that we figured out is that the crypto systems which we are being built for the post-quantum can also be manipulated to have a built-in backdoor. Now, we all know or hear about the backdoors and Trojans, and there has been rumors that in the traditional classical public cryptography, organizations could have put a backdoor that reveals everything about the secret key. And in case of post-quantum cryptography, there is a particular thing which makes it relatively easy for someone to put a backdoor. And what it is, that if we are performing, let's say, learning with error representation or LWE, a kind of lattice-based crypto system, then we do multiply a couple of matrices and then we add an error vector to get the final operation. So this is a noisy system. It's expected that at the decoding part, you will be able to get rid of noise. And this adding is noise is exactly what makes it mathematically very hard for an attacker to get the secret keys or the S out of the system. But it turns out that this particular inclusion of error is what also makes it very, I would say, convenient for someone who is designing the implementation to implant a backdoor. And this is how it works, that if someone is generating the key pair, let's say for the Kyber KEM, then they will generate a value of public key A and T, and there is a secret key S. The whole LWE instance is T equal to AS plus E, where E is the error that's being generated also through a seed. So it's perfectly possible for someone to add a simple payload to this error. Now, this modified LWE instance with the extra error is AS plus E plus D, where this D is coming as part of this payload. And if one looks into the so-called decryption failure because there are too many errors in the system or not, it could be designed in such a way that it will be indistinguishable from a regular LWE instance creation. So one can put this simple payload in a very, very stealthy manner into the algorithm. So that is the backdoor what can put, and the backdoor can also be having its own private and public key so that the payload is capturing whatever secret one needs. For example, this S can be passed through the backdoor payload, and only the person who has the corresponding private key will be able to decrypt the payload. So this is something that we tried with Kyber, and we showed that one is able to recover the key with 100% success rate, depending on no matter how many 1 million key exchanges, no observed decryption failure, and one can keep adding even more information apart from the key, the plain text, and so on. So you might be purchasing a perfectly fine looking Kyber hardware or software from a vendor, and that can contain a payload which will keep leaking information about your internal sensitive data. And this is something very different from the Trojan. We can put a Trojan on top of this to do many more attacks and so on. So with this, I will like to conclude the talk. There are many more things that could be shared, but it will just expand the scope of this discussion too much. What we do see is that the capabilities of quantum computers is definitely growing. And one of the big questions here that everyone, I'm sure, are asking about the quantum community is what is the real impact of the quantum computers on different kinds of application? What we know is it has a real impact in security, and that requires us to take very careful steps to quantum safe security. And this is a situation that we are in where the classical attacks can be done on the quantum computer, which can undermine even if there's a value. For example, one may claim that they are building a quantum machine learning, and I can simply infiltrate an adversarial attack or make a malware or make a side channel to the quantum computer. On the other hand, the quantum computer is trying to grow or scale in such a way that it will completely undermine the public crypto system, forcing us to do the PQC adoption and face all the challenges of quantum migration. So moving forward, we will definitely see a lot of growth in the EDA circuit and system design for quantum, and need to keep balancing the hype and reality. What do we can deliver and what is actually achievable, considering all the practical constraints like memory bandwidth, classical speed up, new classical algorithms. And there is a very interesting research area that comes up is whether it's possible to do quantum attacks on quantum safe cryptography. There is possible that a polynomial time quantum algorithm to break lattice crypto systems or code-based crypto systems, which might put the entire quantum safe community, security community like PQC community at complete risk, and they have to rethink the whole problem again. So I'm very thankful for many different collaborators and supporters of our research in this particular area. We have recently launched a spin-off called PQ Station. You're welcome to visit and share your knowledge and collaborate in this domain, where we are trying to help different organizations to go through the journey of quantum migration and how do you make your system. It's a very, very challenging engineering task to identify which protocols are quantum unsafe, how to do the migration, how to do it in such a way that we have minimum downtime, and how to balance with the crypto agility, how to have a good prediction of when the quantum computer is going to affect the whole thing for real, and so on. So thank you very much for your attention. It took a long step to cover through all the things. Um, I see some comment from Aisha. I'll probably catch with her later because she had to drop out. Okay, so Liang, thank you very much for hosting the talk. If you have or
Yes,
any audience, any questions.
Yes, thanks for such informative talk. Uh, any questions from audience? I mean, you can feel free to unmute yourself or tap your question in the chat box. I mean, I can begin with some questions. Uh, so, first of all, um, back to your quantum security work. I mean, when you propose those attack schemes, malicious attack schemes, um, have you also proposed some like defense, like corresponding defense techniques?
Okay, so you mean this malware attacks and side channel attacks,
Yeah,
right?
yeah, right.
Yeah. So, I mean, for malware, the defense would be pretty simple that you must protect your target CPU, and
Mm-hmm.
we should not be, I would say, casual about the control segment of the quantum computer. And here it includes the CPU, includes the FPGA, includes the direct digital synthesizer. So everything that you see about the setup should be dealt with as critical as you are dealing with a complex industrial control system like a smart grid and so on. So we didn't particularly propose a defense to that, but we do see there are existing defenses that can be borrowed and just put it in here.
I see.
So for this one, actually, it has been a very recent study of us. So we are yet to present the work in Asia CCS. So we did observe this whole phenomenon of swap paths affecting circuits each other very recently, and we think that, of course, it can be avoided by having a better placement algorithm so that it avoids this kind of swap paths between multiple quantum circuits which are co-residing, but we didn't propose the algorithm yet. What we do know is it's not sufficient to have the uh, individual quantum circuits just spread apart, but you need to really figure out that, okay, if they're running concurrently, how the swap path is being formed and whether there is a chance that this paths will overlap.
I see. That makes sense.
Yeah.
Yeah, I actually I do track some security papers. I mean, the either the hardware security for the quantum or some like quantum security stuff like backdoor attack on the quantum federated learning. I mean, this topic seems like recently pretty hot in like conferences like CCS, SMP host. I've tracked several papers, and sometimes the papers propose the like malicious attack schemes, but there's no, I mean, a proposed defense skills. So I mean, since like I think this could be something we can dive into, and probably there's still an open topic to do the research. Yeah, seems
Definitely, definitely,
yeah, pretty promising. And another question
definitely.
is like I found your PQ station, right? Is this
Yeah.
a startup company? I just checked the website.
Yes.
I see. And you've
Yeah.
mentioned the company is looking for the collaboration between different organizations. Could
Yes, of
you?
course. I mean,
Yeah,
yeah. The we already are running several pilot projects
I
in
see.
Singapore, and we are trying to help different organizations to do the quantum safe migration. And sometimes this is mandated by the governments, like you have to develop
Hmm.
your own defenses, you have to have an audit whether your enterprise system is quantum safe or not. And for many organizations, they are completely being caught off guard because these things are very new to them. They don't understand what is QKD, what is PQC, and what is quantum computers. So so what we are now right now looking into is more commercial engagements. Of course, academic collaborations are also welcome, but commercial engagements, like if there is an organization and that they want to try out our tools and our IPs, so it's a very detailed offering. In the presentation, I mostly mentioned about the algorithms and the implementation.
Hmm.
But when it comes to the adoption of the quantum safe migration flow, one of the first things that any company needs to know is uh, how many systems that they have which are actually vulnerable. So we call it as a tool called QVision, which is exploring the quantum vulnerability across the entire organization. And the
I
vulnerability
see.
could be in terms of the network packets, in-house or external, that you are connecting to external servers and you are exchanging network packets. So the network level vulnerability, it could be the database storage level vulnerability, and it could be also the application development environment, like you are developing a new security application and you are calling crypto libraries which are deprecated or vulnerable. So we do this kind of analysis, and we also are offering this tool as a evaluation version for anyone who wants to try it out. That's the first tool. And the second offering is what we call as a quantum safe tunnel. Basically, if you have an interconnect in your organization and you want to just make a small segment of this interconnect as a quantum safe, then we add proxy servers around the interconnect, and the proxies do offer a post quantum crypto key exchange, which means your classical endpoints can still remain as it was, but we add a layer of protection around it, which helps in phase wise migration, because you are not just going to change everything overnight in all your nodes, but you want to do phase wise. So this kind of things we are open to look for, say academic, but primarily commercial projects.
I see. Yeah, it seems like I mean, it's definitely an interesting topic. It's just makes me kind of like a bit surprised. I mean, I've through the LinkedIn, I actually see several startup companies in Singapore working on a quantum related topic, and this is the first startup I've seen working on the like quantum safety. Yeah, I used to see a startup company working on a quantum machine learning, I believe, and I mean, a very interesting thing is like I used to apply for the PhD program in Singapore, and actually I get admitted. And this one student who applied to the PhD program with me with the same year, he graduated and he working in a quantum machine learning startup company. Yeah, but he's
Yeah,
not
yeah,
working on the quantum computing through his PhD study.
yeah. Right.
Yeah, it's kind of surprising me. Yeah, yeah. But
Yeah,
it's great to see quantum is kind of like building up its community.
yeah, yeah.
Yeah.
So we try to keep our foot on both the boats. We try to see that, okay, we will be somehow participating in the direction where quantum computers will actually break crypto system. And on the other
Hmm.
hand, we also try to keep the community safe by adopting and promoting the post quantum cryptography.
I see. Yep. Any more questions from audience?
So of course, everyone is most free to email me if you have any
Hmm.
follow-up questions later.
Okay. If this, oh, yeah. If there's no more questions from audience, let's thanks again for today's speaker, and look forward to see you guys in the next lecture in the QCS, and also have a good enjoy a good night.
Yeah, thank you, Liang. Thank you, everyone.
Yeah.
Bye.
Bye bye.